Let's now have a look at a uniformly charged sphere and use Gauss's law to derive the electric field as a function of radius. In this particular problem, we're going to say that the sphere is an insulator. That is a really important fact because if you were to distribute charge in an insulator, the charge would kind of stay wherever you put it. And so it won't all go to the surface the way that it would for a conductor. We've seen that already. So if you have an insulator, the charge is going to spread out kind of evenly. So if I put a Q, let's say I put a positive Q on this, it's going to spread out like so. And of course it spreads out through the volume, right? I can't really show that here in this picture, but it's going to spread out evenly. So maybe you've made designed a new type of styrofoam, right? And when you make the styrofoam, you end up giving a certain amount of charge to every milliliter of volume, and that charge kind of gets spread out evenly. So that's kind of the situation that we have here. Let's make the radius of the insulator equal to r, and let's have a radius for our Gaussian surface, which is equal to lowercase r. And again, we have a Gaussian surface which is spherical, and so I'll represent that as a circle here. Okay. I'm not going to go through the motivation again for why do we pick a spherical Gaussian surface. You know, that should be obvious from the geometry here. We've got a sphere, so you would want to have a sphere drawn around it or inside it. What I am going to say is that we're going to take the same approach, and we are going to look at radiuses of that Gaussian surface, which are going to be either bigger or smaller than the radius of the insulator. Now, for this example, I'm going to start off by looking at Gaussian surfaces which are bigger, because that's the easier one to do. And all I'm going to say is that if you look at this, the enclosed charge is equal to Q. So since the Q enclosed is equal to plus Q that we put on the sphere, we're going to get the exact same result that we've obtained from the last few examples. So whenever you have a spherical distribution of charge and you're on the outside of it, the electric field is going to be essentially the same electric field that you get from a point charge. So this is becoming a theme, right, with a lot of these examples. And so on my graph here, I guess I could just put this in right away. So if we graph the electric field versus lowercase r, where that's the value of the radius of the insulator, you're going to have excuse me, you're going to have that kind of a curve. Okay. All right, so that's the outside part. See, that was very easy. The inside part is also, I don't want to say it's easy, but let's see what happens here. When you start going on the inside, make this outside. When you start looking at what happens on the inside, it's interesting, because your Gaussian surfaces, the amount of charge that they enclose is going to depend on how big they are. I'm going to draw a Gaussian surface in here as best I can. And you can see that that circle, that sphere, is going to include some of the positive charge, but not all of it. But it's definitely going to have something. So we have to account for that. And so our expectation would be that the bigger that you make this Gaussian surface inside, the more charge you're going to have, and the stronger the electric field should be. So we kind of expect to have a situation where the electric field maybe is going to start at 0 when you're right at the origin, but it's going to get bigger and bigger as you go up. So let's see if Gauss's law confirms that. So we'll write that down for Gauss's law. And we are going to, again, assume that even on the inside of the insulator, that the electric field, due to this inside charge, is still going to be kind of pointing away from the center. In other words, it's going to be on the radius. So we're going to make the standard kind of assumption here that I can take E out because the dot product should be 1, or at least the angle, the cosine of the angle should give me 1. So the dot product kind of goes away because my area vector and my E vector go the same way. Also, the electric field should have a constant value at the radius that I choose because it's the same size, no matter where I am on that Gaussian surface. So that's nice, that comes out. We're also going to do the standard replace dA with 4 pi r squared. And we've kind of explained that before. So now what we're left with is how to deal with the other side of this, because this is the tricky part. The fact that the enclosed charge changes as the radius gets bigger. So we're going to do a little, we're going to do an aside. I'm going to move down here. Okay. And here's what I'm going to do, is that I'm going to assume that if I were to take the total charge and divide it by the volume, whoops, of the object, so Q divided by 4/3 pi r cubed, that would give me the density of charge in coulombs per cubic meter. I'm going to assume that that density is still the same inside of my Gaussian surface. And so that should be given by the enclosed charge divided by 4/3 pi lowercase r cubed. So notice there are some differences here. This is kind of like the global, the whole object, its charge density. This is the local. This is the charge density inside the smaller Gaussian surface. And they should be the same. If this is a uniformly charged object, they should have the same density. And so what we have is the 4/3 pi's cancel out, and I have a nice way of getting a ratio here. Of my radiuses. Okay, so you see what I did is I cross multiplied this little r cubed, brought it over here. I left the big Q, that's the total charge, and then I just brought these things inside of a cube. Okay. So as r, so if r is equal to 0, Q enclosed is equal to 0. That's good. And if r is equal to r, Q enclosed is equal to Q. And that's good. And then in between, it's going to grow like that. So what I'm going to do is use this as a substitution. And that's a Q on top over that. So I've substituted in for Q enclosed. Okay, that was the trick there. And then, let's see, I'm going to divide this stuff over. So I'm going to get my 4 pi that comes over. That'll give me 1 over 4 pi times that. That's K. We know that that's K. And then this r squared is going to cancel out some stuff. It's going to cancel out a little bit of that. So that just makes it an r. And the r cubed remains. That's not a variable, right? And that's Q times Q. Just Q. Okay. And let's simplify that. So that would be K times Q over r cubed times r. And you have to keep your r's straight here, just like a pirate. This is a constant. This big R is a constant. So just think about that as a number. It doesn't change. But the little r, that's the radius of our Gaussian sphere, and that can grow, and that can change, and that's what we graph here. And so what you have here is basically that the electric field is directly proportional to the Gaussian radius, because all this stuff is just a constant. And so that's a direct proportion, and when you graph it, you get a line. And so we now know that inside this object, the electric field grows linearly with the distance r. By the way, when you reach this point here, that value, of course, would be k times q over big R squared. And you can verify that by doing a substitution either for this formula, putting big R in, so that should be the same, or if you make this little r equal to r, big R, then you get the same result. So it doesn't really matter which formula you use, you'll get the same result for the point right there. Okay, so this is a pretty important example, just because we've got a different situation where the charge actually grows as you increase the surface, and the electric field goes linearly. Okay.